Howdy everybody. In this video, I want to talk about the why behind the rational root theorem. So as we get started, we're going to let A, B, C, and D be integers. So that's a fancy way, that funny looking E means element of, and that fancy Z is the integers, the set of integers. So A, B, C, and D are integers, and what we're going to say is we've got two factors, ax plus b times cx plus d. Okay, which, and if this were equal to 0, then this would tell us these are the factors over here. And then the zeros, or the roots, or the x-intercepts, would be the values, x would equal a negative b over a, and then, or x would equal negative d over c, based on the way that I have this set up. Okay, so if we were to FOIL this out, what we have is we have an acx squared, and then we have plus an adx plus a bcx plus a bd, and that's equal to 0. Okay, so these, we have this is a quadratic, and we really have, we don't have 4 terms, we have 3. So we've got, and when you rewrite it this way, you can kind of see a little bit better. You've got your x squared, your x term, and then your constant. So what happens here, the rational root theorem gives you the list of possible rational roots for a polynomial. Well, this is a quadratic, so it's the babyest of polynomials. Well, maybe linear is a polynomial, but those are, anyway. But what happens here, the possible rational root theorem says it's the factors of the constant divided by the factors of the leading coefficient. Okay, I'm too lazy to write that out. So what that means is, in this particular case, our factors of the constant is this BD. Okay, so the possible factors of BD include, well, this is like, if this had been a 5 and a 2, okay, then the factors, that means that this would be 10, and the factors are 1, and then 2, 5, and 10. Okay, so with BD, the factors would be 1, B, D, and BD. You know what? Let me just, I probably should change our requirements. Let's now say that A, B, C, and D, let's change this. As I worked through this, I thought of a better way to say this. A, B, C, and D are prime. Okay, that way that there's not like b over 2 isn't an integer, and that sort of thing. If those are prime, then the factors of BD would include 1, B, D, or BD. Just like the factors of 10 would be 1, 2, 5, and 10. Then we look at the factors of the leading coefficient. So that's going to go on the denominator. Well, the factors of the leading coefficient, since the leading coefficient is AC, the factors of AC would be 1. It would either be A, or it would be C, or it would be A times C. Well, so we're going to divide all of, I'm using color on purpose. We're going to divide all the yellow by all the pink, and then that's going to give us our list of possible factors. So I have 1 that can be divided by, and actually, all of these could be plus or minus. Because I could have a negative A times a negative C, that would give me that positive AC. Okay, so I can have plus or minus 1 divided by 1. I can have plus or minus B divided by 1. I can have plus or minus D divided by 1. I can have plus or minus BD divided by 1. Then I can have, there's more. Then I can have plus or minus 1 over A. I can have plus or minus B over A. I can have plus or minus D over A. And I can have plus or minus BD over A. I can also have, did you notice what I did? I'm working my way through this list right here and then dividing it by one of these at a time. So here we go. We're going to keep going. I can have plus or minus, comma. I can have plus or minus 1 over C. I can have plus or minus B over C. I can have plus or minus, I just got lost, D over C. And I can have plus or minus BD over c. And the last set, based on this rational root theorem, would be b plus or minus 1 over ac, plus or minus b over ac, and plus or minus d over ac, last one, plus or minus bd over ac. And if these are prime, nothing can cancel. Okay, so let's go back and look and see what our actual roots in this particular problem, what they really were. What we notice here is we had a negative b over a, and here is that negative b over a, and we also had a negative d over c. Well, so here's that negative d over c. So that comes from that list of possible, well, those two actual roots come from the list of possible rational roots. So that's a little bit of how this works and why this happens. Let's say, real fast, let's say I give you f of x is equal to, and I say 4x to the fifth plus a whole bunch of stuff that I don't care about, plus 10 at the end. To find my possible rational roots, I'm going to take the factors of 10. So that's 1, plus or minus 1, plus or minus 2, plus or minus 5. I kept using 10. Sorry, I don't know. Plus or minus 10. The factors of 4 would be plus or minus 1, plus or minus 2, and plus or minus 4. So if this polynomial, which I didn't even finish writing, if it actually has rational roots, then it has to come from the list. Well, it's plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. That came from when I divided 1 by everybody. Or I could have plus or minus 2 over 1. We already have, oh no, I lied. Plus or minus 1/2. I forgot what I was doing. It's actually before school, and I'm too tired. 2 divided by 2 is 1, which I've already written down. Plus or minus 5 over 2, I do not have. 10 over 2 is 5, which I already have. Then I have plus or minus 1/4. 2 over 4 is 1/2, which I already have. 5 over 4, plus or minus 5 over 4. 10 over 4 reduces to 5 over 2, which I already have right here. And so this, there's 2, 4, 6, 8, 10, 12, 14, 16. There's 16 possible rational roots. And I've listed what they are. We know that we can't have 16 rational roots because this is only raised to the 5th power. So you'll have as many as 5 rational roots. You will have exactly 5 roots. Some of them might be repeated, or some of them might be irrational or non-real, but there will be 5. So if that's not the color I wanted. If the graph had bounced something like this, like it could do something like that, where this root shows up twice, this root shows up once, and then this kind of indicates to us that we have 2 non-real roots. So we would have 2 plus another 1 plus another 2. We'd have 3 rational roots, but 2 distinct values, and then 2 non-real roots. Okay, we'll talk about this more, but I wanted to kind of explain where that comes from.